We are ready to start. Hello, everyone. Welcome to this course on TCP-IP. It's a real pleasure to see you all in the room. We're not used to that over the past months. So welcome to the course on TCP-IP. Here is your teaching team. I am Jean-Yves Le Boudec, your teacher for this semester. And we have a TA team, Stéphane Plassard, who's helping me in the lectures today, and three other TAs. Why am I missing? Two other TAs, sorry. Pluton and Hossein, and three assistants étudiants, Marc, Dubravka, and Bastien. So they will be helping you online on the Moodle forum, also with the quiz and with the labs. Whom is this course for? It is a course for computer science originally, but many of you are not in computer science, also in communication systems, electricity. It's a course for beginners in networking, although we'll go fairly deep into a number of points. But of course, this is a course on the computer, so you're expected to be at least a bit fluent in using the computer. We will be using virtual machines in Linux. If you've not done that, a lot of that before, no problem. It will be easy we'll give you all the means to start easily. If you're comfortable with that, if you have a Linux PC, then it will even be easier for you. So some programming is required. We will have some labs that require programming sockets. We do them in Python. If you're more comfortable with C++ or some other low-level programming language, it's also fine. And as I said, the lab will be in a virtual environment, so more about that. This course is for everyone. So in the computer networking field, we are strong believers of equal opportunity, and we appreciate and value and support diversity, like hopefully everyone at EPFL. If you had any problem in this course or anywhere in this section on this level, you know that there is the safe space. So there are places at EPFL where you can speak up if anything would happen. The computer networking area is very typical of something that I can say has a description complexity. If you, probably many of you have been trying already to configure a modem or a computer to do something or to connect to Ethernet, and you look up on the internet and you find the to-do list. First do this, click there, do that, and after 12 steps, if you're lucky, it works. Most of the time, it doesn't work because the environment in which you're in is not exactly the same as the environment that you have found on a blog or a forum to do your thing. So this is because there are many details. So the problem in this area, like in many areas of computer science, but very specifically here, is how do we cope with such an avalanche of details? The good news is that those details are not random, the result of random evolution, like in biological systems, where you may have lots or all variants that are possible exist or have existed or will exist in the future. In computer networking, it is not like this. So there is some design behind things. Now, it's a design done by people like us, so we have limited abilities. We cannot do too complex things, so the basic ideas are fairly simple. Of course, when it comes to developing a system or software system in particular, then it's up to the software designer to introduce many tweaks out of the design. So we will see that there are variations, and you have also some software systems that don't use the correct terminology, which makes them a bit difficult to understand and to use because we don't know exactly what they're doing. So there is a trade-off between knowing all the details that we want to know if we want to be experts in this field, and also the limited time we have, and also perhaps the incentives, the desire we would have to learn all of these details. Probably after weeks and weeks of details, you get fed up and you don't want to learn more. At least most people would react in this way. To address this point, it is classical in this field to use what we call the RAKE technology, the RAKE approach. A rake is a tool that you use when gardening that is both wide, it has some breadth to capture, to handle a large surface, and it goes deep, but it goes deep on selected areas. Right? So that's exactly what we will do. We'll go deep, so we will cover practically all aspects of the computer networking field as it is today. And but we will not go deep in every aspect because that's not one, interesting, and second, possible. But we will go deep in a few selected topics. Those are essentially the topics of the labs. So in the labs, you will go in detail into configuring and running some systems where you will need to put your hands into all the details. And the hope is that by doing that, we can interpolate anything you will see in real life later, hopefully is in the convex set of what you have seen today. That will certainly not be exactly true. Hopefully the field will continue to evolve. And next Monday, for example, will be a very interesting talk by Adrian Perrick at 4:15. If you're interested in networking, I encourage you to attend. So you will see that new things, new paradigms are coming, but having done this approach over selected topics and over a wide area would help you quickly understand what those new paradigms are. So this is how we will address this, this apparent contradiction. Another aspect of that, which is perhaps even more important than the RAKE philosophy, and I encourage you to think about it for anything that you're doing at EPFL, but even in real life, it is to separate the questions that you have into why, what, and how. Most of the time, when you go and look up for something on the internet, you have the answer to the how. Because at the end, that's what you want. You want something done, you don't care why this was done, etc. But if you want to be more powerful in what you do, and if you want to invest a bit more in a given field, I think it's important to not be limited to the how, for multiple reasons. But the major reason is that the why and the what are usually very simple, at least for systems that are man or woman made, because we're not able to do very complex things. We do simple things one at a time. Complexity comes from the many of us doing many simple things all together. For example, we will see, why is the MAC layer invented? Why is the MAC address the way it is? Why is Ethernet the way it is? If we ask this question, then the answer is very simple, and then the rest follows almost immediately. So why was it invented? All the things we are working with have been invented by people that then don't come from nature. So why they were invented helps us understanding how they work. The what is also usually much shorter, and the how, of course, then becomes complicated. It has been developed using some environments, some assumptions and some technology. Buffers were extremely expensive when computer networking was made. It's much less expensive now, so things can change. And an important thing also is that the how, after taking a course like this one, in many cases, you will be able to guess the how. Once you understand what this system, what this function, what this software is doing, then you can imagine how you would do it if you had the homework of doing it. And most of the time, the space of possible is not so large. So most of the time, the real stuff is not so far from what you had imagined. And if it is far from what you had imagined, that means, yes, there is really something interesting that is worth spending time on. If it is exactly how you had imagined, then perhaps you don't need to know the how. Perhaps you can leave it somewhere to the documentation and the user manual and the reference guides when you need to do it, but perhaps you don't need to learn it. Wikipedia is, of course, a tool to use for computer networking. It is usually good. I encourage you to go there, and if you see mistakes, to correct them. That's what I always do, but there are sometimes small mistakes that are left over. Depending on the Wikipedia pages, many of them are good at the how, much less good at the what. And this is what makes some of them unreadable. If you start explaining how this is done and blah, blah, and you don't even know what you are talking about, then it makes it apparently difficult. As I mentioned, we will do labs. The labs are very important because this is where you will do for real the stuff that we see here in the lecture. So from PowerPoint to real stuff. There are 7 labs. The last one is only 1 week because the semester will come to an end. They're all mandatory and graded. They can be done entirely in your machine. We used to have special machines with a sandbox in the past, but now that virtual machines for most of you will be very easy to use, then you can do it on your own computer, which also is more comfortable for you. Recently, so all the last year, up to last year, all computers in the world used the same processors, the Intel architecture. So we could do a single lab that could be done by all. Now this year, Apple has pushed the frontiers of technology a bit and has diverged, so has their own processor. And unfortunately, the software that we use for virtualization, VirtualBox, does not yet exist for the Intel machines. Also, the Linux that we use inside VirtualBox will be by nature possibly a bit different on an M1 processor than it is on an Intel processor. So it becomes very difficult for us to support the two. So this year we don't support the Mac M1. We don't know how to do it on a Mac M1 with the software that we have. But of course, now it's bad luck for you if you have only a Mac M1. So if you're trendy and have bought the latest computer, then there will be a difficulty here. There are several solutions. Many of you have a second computer, Linux. You need a even a 10-year-old computer that has an Intel processor is able to do the labs. The footprints are extremely small. So if you have a second computer somewhere that you use as backup or for Linux or old stuff, then you can use it. And if you don't, we will lend you small computer. We have a 68 Minix computers, which are headless computers. We can lend you the computer and also a display and a keyboard if you need. We have also a room INF019 where such computers are. So those of you who are in this situation will need to use or can use those computers as a replacement. The labs, we encourage you to work in groups. That means to talk to each other, but you have to return the lab assignment individually. Some labs have a bonus research exercise. That means questions that take more time. We acknowledge the fact that you have limited time for this course. This is a 6-credit course. The labs are designed to fit in 6 credits. If you're very interested, or if you went very fast in some lab, which may be because at the beginning, for example, you already know Linux virtual machines very well, then you can move on more quickly. And if you're interested, then you can do a bit more. This is what we call the research exercise, and they count for bonus. The lab returns are all automated, so you don't need to fill in paper like we did in the past years. We were boosted by last year's situation to make everything remote. So you will need to give your answers to the lab on Moodle in the form of 3 or 4 blocks of questions. And they will be graded by the computer. So as soon as you submit them, you will have the answer. If you're not happy with your grade and your submission, you can try again. You can try again as many times as you want. Only the best answers will count. And also you will receive more immediate feedback as soon as you have done 1/3 or 1/4 of the lab. So all info is on Moodle about this. I am also a strong believer of learning by small pieces. So to encourage you to do that, to force you, in fact, to do that, we ask you to do a little quiz of 10 to 15 questions every week after the lecture on the content of the lecture. It's also online. If you follow the lecture, it can be done in 15 to 20 minutes. If you block at some point, it may take more, but that's how it is designed. And this is to make sure that you progress all in synchrony, that you've learned the thing that we see at the beginning when we come towards the middle, because it's a lot of little things. Everything is simple, but if you don't get them in place well at the beginning, you may do things completely wrong in the future. So that's to avoid this. This is what we call the lecture quiz. They're online on Moodle too. And we force them to do them in the sense that all the quizzes are chained. In order to do the lab first quiz, to return the first part of the lab, you need to be up to date with all the lecture quizzes that have been done so far. For example, tomorrow, or even today, you can start lab 1. If you want to fill in your results of lab 1, you need first to have done the quiz that follows this lecture, and so on. And this is enforced by Moodle. Those quizzes are not graded in the sense that whatever grade you achieve for the quiz will not count towards the final grade, but they are mandatory. And mandatory means we declare that you've done a quiz if you passed with a grade of 70%. So if you don't, take it again and again until you reach the 70%. When you take a quiz again, if you wait 2-3 minutes, you have a feature of Moodle called deferred feedback. that gives you help on, gives you a feedback on the wrong answers that you've given. So we will know you're wrong because this or that, and then you can try again. You need still to wait 2-3 minutes to think about it. So we hope all those tools will make your learning efficient and enjoyable. So your work every week is to attend the lecture in this form or remotely on Zoom or asynchronously. The lecture is online on YouTube, and then advance and complete the lab. The lab is meant to be spread on 2 weeks, but it's split into 3 to 4 parts, which you can do asynchronously at the time that you want. But we do have lab sessions, 2 lab sessions of 2 hours on Fridays in the rooms that are indicated here. The room INF019 is a special room for those who must use the Minix computers that are available only in this room. Everything I hope will be enjoyable, except perhaps the final exam. So at the end, there's a final exam. The plan today is to have it closed book. That means you will not have documents and no computer, which is paradoxical if you want. This is a topic with so many details and so on. But of course, the lab will not ask you what's the command you gave into the virtual machine to change this configuration of TCP, for example. There will be more at the conceptual level. And we post also an exam booklet, which is the set of all the slides, but contain perhaps technical details, things like what are the names of a field in a TCP or an IP header, and so that you will know what you don't need to know by heart. And of course, there are the exams of the previous years are posted, so you can have an idea of what kind of things you can expect here. So the exam is essentially putting you in simplified situations that correspond to the labs, to the different labs. And then we ask you questions, or how will this protocol work? What would this protocol do? How would you solve this misconfiguration problem? That's the current plan. Now, last year we had to do something differently. Last year we gave an exam that was done remotely on the computer. And the way to do it was to, in fact, Stefan, to program individual exams for everyone so that we avoid cheating. But that was 2 months of development. So if we can avoid this year, we'll try to do it the usual way. The grading gives equal weight to the theory. That means the exam and the labs. And the labs are weighted by their duration. The last lab is a bit shorter, so it has a weight that is half. And the research exercise bonus is added to that, but of course cannot make the grade exceed the max. And we grade always in row scale. So if a lab has 10 questions, perhaps it's graded between 0 to 10. And it's only at the end that we convert to this strange EPFL scale from 1 to 6. And all the grades we give are always exact, not rounded, so that there is no side effect of this rounding system of EPFL. Voila, that's for the introduction and the mechanics of the course. Are there any questions? Yes? Are the lab sessions mandatory to attend? No, the lab sessions, the question is, are the lab sessions mandatory to attend? No, so the labs are assignments you have to do. You must do them on the Linux computer, which can be in your virtual machine in your computer, or on the Linux computer that we give you if you don't have any other means. And then you need to do experiments and give your answers on Moodle. You can do that from anywhere at any time, provided it's done for a given deadline. The lab sessions are really sessions where we help you. We are present in the room to address your questions. Of course, we are also present on Moodle for the entire week during working hours. That's in particular the jobs of the assistant étudiant will be to attend the Moodle forums, where you're encouraged to ask questions and to work at whatever point in time you find more convenient. Other questions? Yes?
Yeah, so I didn't catch it. You said that we can repeat even lab quizzes more than once, or
Yes, when you do a quiz, you do a number of questions. Yeah. And when you've done all the questions of a given quiz, you can submit the quiz.
Okay, that's it.
No. Then you submit, then you have a grade. You see your grade instantly, or after the computing time of the computer. If you're not happy with the grade, you can take it again. Which may not be a good approach to just try, do it until you, I think it's more intelligent to first to understand what and give the right answers. But we want you to have as pleasant and as efficient an experience as possible. Yes? Well, there are 2 lab sessions for scheduling reasons. We really have 4 hours of lab sessions, and due to availability of the rooms, and also because we have seen the hour 3 and 4, usually we need a smaller room because there are fewer people. So we have the very, very big rooms during 2 hours, then smaller room at hours 3 and 4. But no, you come whenever you want. There's no difference. As I said, in the lab sessions, we will not say, okay, now, because we don't use, I mean, everyone has their own hardware. So you do the thing at the time you want. You don't need to do a special thing at a given hour. Other questions? Yes? Yes, here. The question is whether it is possible, if you are using Linux routinely, whether it's a good idea to use it on your native machine. Perhaps, Stefan, you have an answer to that?
With the quizzes aligned to the virtual machine. So some questions need
I think, strictly speaking, it is possible to do it on your machine. If among the zillions of variants of Linux, you happen to have one that has the same name and the same commands as the one we use, which we use a variant of Ubuntu. So it's quite possible that you have something very similar. Still, there is, I mean, you may break things in your, because you're playing with your experimental things, so you may break things. It may be a good idea to protect, if you really use the computer to do other work that is important to you, it may be a good idea to protect the rest of your computer. For example, you change the TCP version and things like this, and you don't want this to happen when you really work to go to Moodle, for example. Yes?
If you will have the lab session tomorrow, you will finish the first lab today, or what is the functionality or content for the tomorrow's lab session?
Say it again.
I mean, if we will have the lab session tomorrow, should we finish the first lab the same day, or just before tomorrow?
No. So the thing you need to finish before starting the lab is the lecture quiz. So after this lecture, you should go online on Moodle and take the first lecture quiz.
But what is the functionality or content for tomorrow's lab session?
It's online.
Okay.
It's on Moodle. So the lab is on Moodle. You can already go and see what's inside. But the course is designed in a way that first you attend the lecture, then you start the lab.
Got it. Thank you.
You're welcome. Question?
So you mentioned we can work in groups, but I think you didn't mention who's the size.
The groups are informal. We're just saying if you talk to someone, if you work with a friend or 2 friends to do things, that's fine with us. But that we don't need to be aware of it. Of course, we might see some similarity in the answers and so on, but that's fine. So the idea is that, yeah, usually you're not alone when you work on the computer. If somebody knows or can help you with something, it's fine to get help from friends rather than from TAs. Right? It's also more scalable given the size of the class for us. But there's no concept of groups in the grading system. You have to give your individual feedback. Good. Then we move on to the very first lecture. So we start by easy things, so that one will go fairly fast. That's what I call the TCP-IP architecture. That means we will cover practically everything in 1 or 2 hours. But why we do this is because by nature, we need to have the global picture first. We will talk about a number of things, and TCP/IP as we will see, is fairly cleanly designed, but still there are dependencies of some things on other things that need to be done immediately. So don't be afraid that this looks perhaps too simple today, but I think if it looks too simple, that's a good thing. I use as a reference book this textbook by a colleague of Belgium, Olivier Bonaventure. Oh, we lost the... So what happened? Yes. So second attempt, yes. I'm using this book as an additional reference for most of the content, which is an online book that's also available for free with the source code. If you want to modify it, you can, which follows very much the same approach as I'm following in this course, which is trying to understand the principles and go from the principles to how they are implemented rather than the other way around. So the goal today is to put in place the different pieces that are addresses, names, MAC layer, IP layer, transport layer. Those are things that we will use all the time. So let's start with that. TCP-IP is a layered architecture. Sometimes you see architecture means the set of rules that are decided by the IETF, Internet Engineering Task Force. This is an entity that decides, for example, which bit is where in the IP header. Or if you want to invent a new version of TCP, then you have to go through it. So it defines the rules. It doesn't define how the thing is implemented in a machine. Nobody defines that. If you do open source code, then you put your design and other people might change it or criticize it. The architecture does not define how TCP is implemented. TCP, for example, is implemented in operating system software, but there are also integrated circuits that implement TCP in devices, in embedded devices. And there are also on some fast computers, there is so-called TCP offload. There is some hardware elements in the computer architecture that implement some functions of TCP. So where the thing is implemented varies, depends on the technology, depends on optimizations that are done, and that changes over the years. The architecture tends to change much, much less. So that's the good news. The architecture is layered. What does it mean to be layered? Well, it means we put boxes and we put some boxes on top of each other. So boxes are what we do when we do any complex system. I mean, this is a huge software system with a bit of hardware for the physical layer. How do you do huge software system? Well, by defining modules and interfaces. So that's exactly what it's about. With one special tweak here, it is that by nature, when we communicate, when my computer sends a file to another computer, the two communicate, that there is two interfaces. There's the interface from my computer to another computer. And there are also interfaces inside the system from a function in my computer that talks to another function. So you communicate with other functions, which is very typical of software systems, but you communicate also with what is called peers, systems that are like you, but somewhere else. So because of that, we consider that there is an interface from A to B and an interface inside the machine, and this is what, for me, layers mean. For example, the application layer, which is the software that does the thing that we want, Facebook, internet, web browser, etc. That's the application layer. It communicates with other application layers, and the thing that happens when we communicate is called the protocol. The protocol is the rules of the game. For example, the web protocol is HTTP or HTTPS, and it says what you do to get a file from another server. For example, you send a GET, you first open a security association if you use HTTPS, and then you send messages like get the name of a file and how the file is encoded, etc. All of this is part of the protocol and the format also. So the protocol HTTP is very simple. It says essentially you send get and you have reply, which is simply the thing you want, the object you want to get. This is the protocol. That's the interface between two application layers of the same application layer, of the same application. And that's the interface between two that are at the same level, typically a web client and a web server. The application layer also uses the transport layer. When you code an application layer, you have to send data. We will see, and you know that data is sent using packets. So when you send a packet, how do you send a packet? You don't have a packet when you have a video file, for example. So you need to send this somewhere. So this is done using the transport layer. So the transport layer is the set of functions in a computer or a device that provides a service to the application layer that allows the application layer to communicate with other machines. So it hides the network. It exists in TCP-IP in two versions, TCP and UDP, hence the name TCP-IP. Why two? Well, the differences are historical, and in reality, there are zillions of variants, but the only two ones that have survived to the evolution today are TCP and UDP. UDP is the most basic one. It is simply giving a programming interface. So instead of being exposed to the hardware, like you do in some industrial networking systems, or if you have an old style field bus that communicates with a sensor, you need to send low-level commands that are very specific of this sensor and this field bus. But in UDP, in TCP/IP, we don't do that. So the UDP interface will abstract from the programming that you do in the application layer using what is called sockets. So you will write into a socket. We'll come back to that in a few more weeks. It's very much like writing into a file. So you will not have to know the physical details of the hardware. And that's the minimum thing that UDP is doing. It is adding, the only thing that UDP is adding is, apart from encapsulating the technical details, is adding the concept of ports that we will see in a few more seconds. In particular, UDP does not attempt to repair all the bad things that happen in real world when you communicate, which is that things can go wrong. Like, for example, my slideshow, the beamer was not showing the display. When you send information over the internet, it's put into the form of packets. Some packets may be lost for zillions of reasons. A radio error over the Wi-Fi link, buffer overflow, because the internet is a huge queuing system, and we cannot guarantee that all the queues never overflow. In fact, they very frequently overflow, so we do lose packets over the internet. UDP will not do anything about that. It will allow you to send a message. If this message is lost, well, it's up to the application to handle the case. That's what happens with UDP. Of course, for most applications, like when you go to a web server and you ask the web server to download a file to you, you don't want to handle all the cases where something is missing. You don't want to do that as a programmer of your application. This is why TCP was invented. So TCP, the primary function of TCP is to hide to the programmer all the details that come from the fact that the communication is not reliable. So it transforms an unreliable network into a reliable communication mechanism. How it does that? Well, there are zillions of details on TCP. It does also other things that are called congestion control, that are completely different stories that we'll talk about later. So TCP will be the topic of many hours of discussion in this course. For now, what we need to know is that there's a small subtle difference between UDP and TCP, which is about the nature of the interface that is given to the application, the socket interface, if you want, the programming interface. UDP considers messages. So if for example, UDP is used by DNS. We'll talk about DNS in a few more seconds. DNS is a set of servers that are able to translate names into addresses. So I send a query, what is the IP address of www.epfl.ch? I send one message to a DNS server. So UDP is used for that type of things when you have a single message to send. And since I am sending a message that in principle should trigger an answer, if I don't get the answer, I know something went wrong, so I will try again. So that's a place where anyhow reliability will probably be handled at the application layer. UDP uses the concept of a message. So if I write some program and I call a UDP socket and I write into the UDP socket, send this message, I know that the UDP will consider exactly this message, which seems obvious, right? But this is not what TCP does. If you write into a file, for example, byte by byte, if you have two messages to send, to write into the file, you need explicitly to say where the first message ends. That's what happens when you do things byte by byte. In UDP, you don't need to do that. If you send two messages to a server using UDP, UDP will deliver those two messages to the server, and the server, when it will receive the messages, will need to do two calls to the UDP socket and will know where the messages start and end, which is the natural thing to do. TCP does not do it like this. TCP is a simulation of a file where you write byte by byte into the file. It is called the stream service. TCP delivers a stream of bytes from a client to a server or vice versa, which is historically given. Of course, people have tried over the years to make a variant of TCP that doesn't do that, but this is how TCP does it today, and we will have to live with that. In particular, the grouping of data into blocks is done by TCP. For example, if a client sends one short message to a server, then a few fractions of a second later, a second message, perhaps in fact TCP, which is, for example, if the communication adapter is very busy, TCP knows I don't have time to send the first message, I need to wait. And here is a second message to send to the same destination. Then it's more efficient to put the two messages in one single bigger message if the messages were small. Why is it more efficient? Well, because when you send a message, there's a lot of overhead that we will discover in detail in this course, things like IP headers. So if I send 1 byte of information to you, I still need to send probably 60 bytes of header of overhead. So if I send 1 byte followed by 1 byte, like some telnet applications where you echo a character that's typed remotely, then perhaps you don't want to send small messages in in individual packets. You want to group them together. That's what TCP does. That's called the stream service. Whether it's good or bad is not always clear. It's good for optimization when you're on very low performance networks like Zigbee networks, Bluetooth, etc. On higher speed networks, perhaps it's more a nuisance than a help, but this is how it is. There is also a new thing called QUIC, relatively new, which is a replacement for TCP, which is probably when you run YouTube, you probably are using QUIC because this is launched by Google, and most Google applications are using QUIC when they can. QUIC does not work everywhere. We'll talk about that. There are limitations to when it works. And it's a kind of super TCP that is more powerful than what I just said. In particular, in QUIC, you can design things. You can have, still is stream oriented, but you can have multiple streams so that you don't confuse two things together. We will come back later. Practically, QUIC uses UDP. So when you do an analysis of the traffic with QUIC, you will still see UDP. For right now, what we need to remember is there is UDP and TCP. Question?
Are all the specifications of QUIC open, or is it just an API from Google?
Are the specifications of QUIC open, or is it an API from Google? We'll come back to that much later in the course. They started as proprietary work from Google. They did an open source implementation of QUIC, which is not the best one. They kept the best one for themselves. But there is now a working group at IETF that is standardizing QUIC. So QUIC is becoming a standard. That's exactly what happens. Whenever something becomes important, you want to make it a standard. And the way to make it a standard means make it part of the TCP-IP architecture is to go to the IETF. And so far, this has always been done. So even Microsoft, even Google, they still go to IETF to make their things standard and interoperable. One thing that is exposed to us everywhere, not just in the transport layer, is the port number. So the port number is something that the application layer needs. A port number, every layer needs a way of addressing. Addressing means identifying which device or which software component in a device this is for. So this piece of information has to reach a given entity that needs it. I'm showing here, for example, two machines, and the machines have, to simplify, several processes. The granularity may be smaller, it may be threads inside a process, maybe even objects inside the thread that may communicate in parallel or in quasi-parallelism. So typically a given machine has more than one process. So when a UDP receives a message, it needs to do to which entity in the machine it has to be delivered to. In order to know that, there must be a number somewhere, an address of this process, and this number is called a port number. For example, if the process is a DNS server, classical servers that correspond to standardized protocols have predefined port numbers, and all the numbers between 1024 are typically are supposed to be those predefined port numbers. For example, port 53 is for a DNS server. So when you send a packet to a machine over UDP to destination port 53, it means that you're making the assumption that there is a process on the server that is DNS server function, and this process will receive everything that is sent to port 53. On your machine, when you send a packet to the DNS server, the port number is not a unique and well-defined port number. It's a temporary port number that's given to you by the operating system. You have your port number. Why do you need a port number? Well, because when the DNS server will respond to you, this response will come to your machine, and then the operating system needs to know to which process inside the machine or to which entity inside the machine it needs to deliver that piece of information. So it will do that using the port numbers. Now that was for the transport layer. So the transport layer, as we have seen, is the mechanisms that allow software to use the network. And when we use the network, as in the example before, we send to a destination port number and from a destination port number, from a source port number. Now, in order to interconnect all the devices in the world, you need some mechanisms. So a stupid mechanism would be to do a full mesh and pool radio links or physical wires between all machines in the world. Well, of course, it's not at all feasible, but mentally, this is what the network layer is doing. The network layer for us is IP, and because direct connections are not possible, we need to be smarter. The very first computer networks were not at all the way they are today. They were using even the very first versions of what was called NDP, that was before TCP-IP. So the first ARPANET was not using TCP and IP. It was using something called store and forward. And the very first commercial networks were IBM as SNA in the 60s. They were using store and forward. So at that time, computers were big things that by today's standards had very low performance. And if you, for example, would send an email from A to B, then the mail or the file that you need to send was first transferred to a first computer, received entirely, then transferred to yet another one, etc., until it reaches the end. So in some conditions, when there are bad internet connectivity or emergency scenarios or revolutions or things, you can still use that kind of things, which is called UUCP, Unix to Unix copy. That's a variant of this, where you can copy from one computer to another computer, close the connection, move the computer, perhaps come in destination of another computer and transfer it, etc. That's called store and forward. This is how the very first computer networks were. Then, okay, so the entire message needed to be transferred. Then came Louis Pouzin, who invented what is today used by all computer networks and all networking systems, called packet switching. So the idea, which was by today's standard very simple, but okay, somebody had to invent it the first time, is to break, instead of transferring an entire file, we break it into pieces that are not too big, that are called packets. Now they are called IP packets. The very first one were the CCLAD packets. At about the same time, 1 year later, Internet, the ARPANET at that time, moved from the store and forward paradigm to this new paradigm where we break the things into packets instead of sending them entirely. So what is the difference? Well, if I send a mail or a video file, say a big file, from one place to the other, perhaps they will still need to go from one mail server to another mail server, right? But in order to go from one machine to another one, they will go through those round boxes in the middle, which are now new machines that were invented by those people, Louis Pouzin and the TCP-IP architecture people, Bin Cerf and Rob Kahn. They are called routers. So routers are, at the beginning, they were computers, just standard computers, but that instead of transferring entire video or images, which by that time were very small anyhow, they would simply transfer the packets. So they would not understand what's inside the packets, because if you have only a small piece of an image, that's practically of no use to you, but they would transfer those packets. So this is called packet switching. And I will conclude this first hour by asking you a small quiz. Why do you think that this happened? Now, of course, you don't use Zoom. So who says answer A, it reduces buffer required in routers? Cool. Who says B, it reduces the bit error rate? Not much support for this. All the performance is very important, and we've seen that we can lose packets because of bit errors. C, it increases capacity. Okay, some support for it. Thank you. Well, the correct answer, so can we close? The majority online says the same as you, and the correct answer is answer A. And here is the explanation. This explanation is interesting per se also because we see here a diagram that we will sometimes use. If you want to analyze the performance of protocols, here's a view. It's called a time and space diagram. On one dimension of the horizontal dimension, I'm showing space. On the vertical dimension, I'm showing time. On the left, I'm showing store and forward. I send a message, and you see that it takes some time to send it. The time it takes to send it is given by the bits per second. If I send it at 1 megabit per second, it will take 1,000 times more time than if I send it at 1 gigabit per second. That's the number of bits per second give this. And then you see that the message takes some time to reach the next hop, which is in that case a store and forward computer. It's not instantaneous. That's because of propagation speed, the speed of light. Things are not instantaneous. They're very fast, but everything is fast in the computer world, so they're not instantaneous. And then you receive it, and then you send it forward. If you compare to packet switching, you see that on the right, you do the same thing, but as soon as you've received one packet, you can transmit it. So where's the difference? Well, the difference in the time it takes, the end-to-end latency is much less in the second case, because in the first case, you need to receive entirely everything. And second, and that was probably the major reason at this time, the amount of thing that is stored in the middle box, in the first case is the entire video file, in the second case is just one packet at a time. So as soon as it receives one packet, it can get rid of it, of course, in this simple example. So this reduces the buffer requirements, which was, and still to some extent is one of the key bottlenecks in the internet today. Voilà, that's all for this first hour. We do a break.